Yeah, so hi everyone. Let's get started. I think, uh, yeah, most of you are here. Yeah, folks. So basically, this talk is about mostly focusing on the implementation of Upserts and the V2 engine in Pinot. But since some of you are not familiar with the basics of Pinot, I'll cover that as well to lay the foundation for the rest of the presentation. So basically, what is Pinot? So Pinot is like a OLAP database, but what distinguishes it from other OLAP databases is the fact that we have designed it to be first of all able to consume real-time data, and second, like we have designed it to basically serve queries at extremely low latency. So basically, most of the OLAP databases are designed to answer queries on like terabytes or petabytes of data. And due to that, their nature is that like each query takes around a few seconds to execute. But in Pinot, like that is not the case. You can serve the same level of data at the same scale, and like your queries will be answered in like milliseconds. And how do we do that? The way we do that is like we allow people to create like various type of indexes that accompany the data, and you can even write your own index implementation and like contribute to Pinot. Or if you don't want to contribute, just run it in your own cluster, and like it will make your queries like extremely fast. Yeah. So we a lot of large companies already use Pinot. Stripe, Walmart, Uber, Razorpay, Grofers are like some of the largest ones which have like petabytes of data, and like some of them even have like 1,000 nodes cluster to serve the queries. And yeah, so next I'll cover like the basics of the Pinot architecture. So since some of you all are not familiar with it, so basically Pinot design has been inspired by the separation of responsibilities principle. What we want is that like each component of Pinot only does a subset of the task, but it does them really well. We don't want a single pod or a node, you can say, to handle like multiple tasks. This basically allows us to easily scale the servers. So for example, if your consumer is slow, you can simply scale the servers, and if your queries are slow, you can simply scale the brokers. If they were tied together, then like you will have to scale both of them, and like that will be just not cost effective. Like you'll have to, for example, you can have two core machines for the brokers while you can have like 16 core machines for the servers otherwise. And that would lead to, if we combine both of these together, it would like really make it not worthwhile to basically scale up the cluster and down the cluster. So how do we do that is basically we have like few of these components. So the most important one is the servers, and most of this presentation we are going to talk about the servers only. In the server, what servers do is that they actually store the data in Pinot, and that data is stored in two places, either in a deep store, which can be like S3 or Azure Blob Storage or anything, and then in the local disk. So why is it stored in the local disk? It's because it allows us to query the data faster rather than like waiting for data to be downloaded from S3 and like you run the queries on top of it. And how is the data stored? So basically, whatever data you ingest into our database, we compile it into short files called segments. And segments are nothing like they are just basically tar files, you can say. And each tar file contains your raw data as well as like it contains indexes and like it contains some metadata. Metadata can be like, okay, what are the maximum and minimum length of this column? What is the latest timestamp present in this data, and so on. The next component we have is the brokers. So brokers are where like people run all of their queries. So whenever you run, for Pinot supports both gRPC query and like normal SQL queries. So if you fire up a query, it will go to the broker. And what broker does is that basically it will create a query plan from that query, The query plan looks like, okay, from which server do you have to fetch the data, from which servers you don't have to fetch the data, what segments you can completely filter out while reading the data, and so on. And so once that query plan is created, it is sent to basically broker start sending the request to the appropriate servers. And the servers process those requests and respond back with the actual data. Once all the servers have responded back with the actual data, the broker does the reduce step. It combines like all of the data. For example, if it's an aggregation query, it will sum up all the data. And if it's like simple select query, then it will just append all the data one by one and then return back to the user. The third component we have is the controller. So controller is the most important component in Pinot. It is basically responsible for coordinating the whole cluster. So for example, we have designed Pinot with redundancy in mind. So it can happen like one of the servers goes down or one of the brokers goes down. So what should we do in that case? Like what happens to the segments on those servers? So what controller does is that like with the help of Helix and Zookeeper, it will say, okay, server A has died down. It was hosting segment 1, 2, and 3. So now let's see which servers are actually alive. And whichever are alive, it will assign those segments to those new servers. And like there are other more heavy responsibilities as well. Like, but this is the basic task of the controller. And so to do this coordination, it requires Zookeeper. So in our Pinot architecture, we use Zookeeper mostly as a message queue and metadata store. So metadata store use case is pretty common for Zookeeper, like where you need to ascertain, okay, which is the leader, which one is not the leader, what uh, what are the latest offsets consumed by the servers and so on. But the queue use case is something like we do with the help of Helix. So what we do is that like we have like large JSONs in Zookeeper, and where we push the messages, or those are again the JSONs, and each message indicates, okay, what operation needs to be performed by what pod. And once that is done, like the appropriate pod consumes that message and like completes the operation. So that's how like coordinator can control like all of the pods. But it does that indirectly, not like directly via API calls. So it doesn't need to bother by keeping the track of like each and everything, and creating like long-term connections with all of the pods. And final, we have like a Minion. Minion is like an optional component in Pinot. It is mostly used for ad hoc tasks. So, for example, you want to schedule a cron job that consumes from S3 or like big table at end of the day. So you don't want something to keep running on like on the side daily. So what we do that is like we take the help of Minion. Minion will like simply spawn up at the time of the when the cron is about to run. They support auto scaling as well, so they'll scale up to like whatever maximum resources you specify, or like whatever is necessary to run that task. It will simply, for example, if you have scheduled a S3 ingestion task, it will consume from S3 and do all the like data transformation operations, and like finally create the segments and like publish them directly to the deep store, which can be again S3. So and then like once it has completed its job, like it can like go into the rest state and like basically saving your cost. Earlier we used to do all of these operations inside server itself, but like that led to a lot of scalability issues, especially like when servers are scaled up to consume like for example 100K RPS of data, and with Minion like you want to consume from S3 which has like 10 billion rows. So you don't really want to scale up servers just to consume data for like 1 hour. So that is why like we separated it out entirely into a new component. Shobhit has one. Is it similar to Hive's architecture? Any differences? Um, I'm not like entirely familiar with Hive's architecture, but the major difference is like Hive doesn't basically Hive has the metadata store, but the actual queries are still performed on the S3 data, which is why like it takes a lot of time. And Hive is not really designed for the real-time consumption, whereas Pinot is designed to consume the real-time data, like from Kafka Stream and anything. So that would be the major difference.
Question on the indexes. So the
Yeah.
indexes here, are they stored as segments or are they like in memory?
Yeah, they are stored in the segments only. Like they are separate files. So we have some raw data file, and then we have the indexes file. So, and you can configure them as the part. So basically, we have the concept of tables, and in table you can specify, okay, what are the indexes that need to be created and on which columns they need to be created. So for each of these columns, we'll have a separate file, although we like combine them together in the end into a single large file, but like that is the general concept we operate by. Keeping
Got it.
yeah, so we, in most of our use cases, we rarely like use any heap apart from like running the query. We mostly use like mmap, and in mmap, like you have to have a file on the disk which you can directly read, even for the simple consumer task. So yeah, so mainly like what are the differentiators in Pinot? So mainly there are like four differentiators: upserts, V2 engine, tiered storage, and the data manager. So we'll cover like two of these today, upserts and the V2 engine, and like how, like basically what use cases they are designed for and like how they can help you. So yeah, so upstart almost everyone who has worked with databases is familiar with upstart. Like it's simply like instead of like inserting new data, you just want to update any existing data. You just take the primary key and do set on column A, B, and C. Now that non-trivial part is like almost every OLAP databases doesn't support upstart. And the reason for that is the OLAP data is generally stored in S3. And like you mutating the S3 files is like extremely expensive operation. Like you'll first have to download the file, then you'll have to read the whole file, then you'll have to find the place where that record is located, then you'll have to basically you can't simply update that file. So you'll have to create a new file with the updated record and like publish that to the S3 again. This can take like seconds. It won't complete in milliseconds. Like if you have like files of size like hundreds of MBs or GBs. So that is why like none of the OLAP databases support it, but we do that in Pinot, and I'll explain you like how do we avoid this like expensive update path. So with the help of Upsert, like we are able to support a lot of use cases. So for example, we are able to support the TTL use cases where you want to simply data to disappear after a time. We are able to support CDC use cases where you want to plug in Divisium or some other thing from MySQL, Cassandra, or anything, and simply want to replicate that their data to the OLAP store. And then in the upserts itself, we allow like out of order updates. So you don't really like need to publish the data like in the exact same order. You can simply say, okay, uh, basically you can just specify some comparison column, and on the basis of that we'll take the decision, okay, which of these rows came first and which of these rows came later on, rather than assuming implicitly from the stream the data is coming. And then like finally we have the partial upserts. So partial upserts are like by default upsert implementation is you can say, okay, we have this primary key A and this was the previous row and now update it to this new row. But the partial upserts allow us to do some other things. So for example, you can say, okay, this is the primary key. This was the value of column A in the old row, and this is the value of column A in the new row. Please sum those values up and like update the next row. So this is a lot of people use this in production. So yeah. So now, how do like upserts work? Like entirely, like how do we avoid that like expensive path? So in that, like basically, so first of all, like how does even consumer works in Pinot? So consumer works in the so basically when you create a table, right? Like and you want to consume data from Kafka, for example. Suppose that Kafka topic has like three partitions. So what we'll do is that we'll create three consumers, and those three consumers will be assigned to like based on the number of available servers. Like if you have three servers, they'll be assigned to three servers, like one server and then a single consumer. Now that consumer will simply like in normal fashion, it will start reading the data from Kafka, records one by one. And like once it has consumed, for example, like let's say 10,000 rows, it will decide, okay, should I need to transfer this data into a segment file or should I keep on consuming? Now that threshold is like configurable in the table itself, and you can specify basically on the number of rows or on the time interval. So for example, you can say after every 12 hours, you need to like basically publish a segment, or you can say the amount number of bytes. You can say like after you have consumed, for example, 100 megabytes of data. So you just publish that data uh, to the basically the deep store. And so this is your normal like consume loop. And inside like each consumer is just a simple like a while loop that keeps on fetching the data and like basically storing it in an mmap backed file. What happens is that like it Pinot also keeps track of the offsets till which it has consumed the data. So for example, it will know, okay, from this Kafka topic, from this partition, I consume data till the 100 offset. And so once it publishes a segment file, it will basically start the new consumer from like 101 offset. Uh, it doesn't rely on Kafka or any other like streaming consumer to manage the offset. It does that individually. And like it stores that information again in the Zookeeper. Yeah. So any questions on that? Then I'll cover the upside part. Sailesh, what is the sweet spot of Pinot in the world of evergreen big data, which we have to choose? What would be? So basically, Pinot is designed like when you want basically la OLAP queries. So OLAP queries are basically the analytics one. So for example, you want to know how many bookings happened in like last 1 year or something, but you want to run those queries at like the basically consumer apps. You don't want to run them on the basically for the analyst or like for like some report internal metrics reporting. So most of the people that use Pinot are for such use cases. So for example, Uber or Grofers use it to show like how many riders are active in a particular area, how much inventory is left, and so on. And like those queries are not like run on like last day of data, they are run on like last 6 months of data. So they are like pretty expensive, and like any other database, like either will be too slow if it's an OLAP, and if it's OLTP, like since it doesn't have data in columnar format, again, like it will be too slow. So yeah, so that is like the sweet spot of yeah, but Cassandra and Solar, like if you use that, right, like most of the people, what they do is that like even people use Elasticsearch for the use cases which they use Pinot right now. And it was pretty expensive. Like Cisco and Uber are great examples of it. And you can simply like read their blogs. And what happens is that like to get started, like they are like pretty easy, and like most people prefer that. Even like we suggest them to like if you want to start with like just start with Elasticsearch or something like that and see like how far you can go. But after a scale, like the cost becomes too large, like and like you have to come up with some optimal solutions which doesn't support like the breadth of use cases which Elasticsearch serves, but you can like support a small number of use cases which like lower amount of cost. Pinot is capable, yes, it is. We have like JSON indexes, then we have like text indexes for which we use Lucene and stuff like that. So that's not an issue.
Question on
Yeah.
the upside in the event stream of Kafka. So I
Yes.
didn't fully understand. Uh, like when would we want to do an upsert in an event stream?
Yeah, so for example, like you have a event stream coming which has like a status of the booking. Okay, so for example, you have a restaurant that publishes like what is the status of this particular order. Like it is now it is in the cooking process. Now it is being it has been picked up by the rider. Now it is being it is in the delivery process. It has been delivered. So what people want is that like rather than like doing on the query side, the filtering, they want like directly to update the data inside the database. Like they don't really want to, and the reason they want to do that is like to keep the query time like really low. Otherwise, like it will shoot up into second. And
But
another like major use case is the CDC. So where you have to plug in some database and you simply want to replicate that database continuously into your OLAP store for analytics. And databases can have like deletes operation, updates operation, and everything. So you need to have like similar operations inside OLAP as well.
right, at the end, the upsert is going to happen on the not on the stream itself, but on the segment side essentially. Like the final column that we store, insert is going to
Yeah.
happen there.
Yeah, that I'll explain. Like, how do we do that? Like, it's not really like straightforward because
Right.
if we modify that data directly, like then like it will be an expensive operation because each segment is like around 200 MB in most of our use cases. So we have to read that, update that for each and every rule, like it will take
Mhm.
really long. And
I see.
we are not like you can only upstart the data which you have recently consumed. You can upstart like any keys you have consumed like since that table is running. So yeah.
Got it. Okay. That's
Okay. So yeah, so basic like our upsert implementation is like in the when we consume the data from the Kafka. So we do two things. Like on the left side of this diagram is a normal flow where we simply like run a while loop, keep on consuming and like keep on publishing the segments. The new flow which is introduced in Upstart is the metadata manager. The what metadata manager does is that like you can simply think of it as an hash map, and that hash map contains like a mapping from the primary key to where that latest record for that primary key is located. So, for example, it will say, okay, for primary key A, the latest value is located in segment B at row number 33. Like that is what it is essentially storing. And so we keep this metadata like E needs to be kept in memory. And like we do support like some off-heap implementations as well, like where you can dump it into disks to save on memory. But by default, it is just kept in memory. And what we essentially do is that like on when we update the metadata, we also have a bitmap, and that bitmap is at each segment level, and what it simply indicates is like which of the rows in this segment are like basically in the latest state and which one are not in the latest state. So it is just for you can simply think of it as, for example, if a segment has 10 rows, this bitmap will be of the size 10, and it will have just values 1010 for 0 for which are not in latest state and 1 which are in latest state. Now, when someone runs the query, so you can see here we haven't actually modified any data in the segment when upsert has occurred. We have just modified this right side, which is always in memory. And so when a query is run, right, what we simply do is that like we simply read the data from the segments or every data like which is valid for the query. And then we have these bitmaps. And what we do is that like we simply filter out the rows for which bitmap is 0, which indicates like these rows were actually are not in latest state. Maybe some other segment has that. And like that way we are like able to quickly run the queries without like, and also able to like update the data quickly because we are not actually doing anything like any mutable operation. We are just like modifying some metadata. Yes, Shobit.
yeah. Yeah, maybe you explained it for simplicity, but just wanted to understand, like, keeping metadata in memory.
Yeah.
It's kind of like, how would you maintain consistency if your server kind of goes down, you come up with a new one,
Yes.
consumer.
Yes. So yes. Yeah, that is a good question. So what we do is that like with each segment, like if a server goes down or anything, right? So we can recreate this metadata, and our servers keep on going down like a lot, like because people are the architecture has been designed like you can simply upscale, downscale like anytime, like you don't need to bother with it. So what we do is that like we have this valid doc IDs, right? So this bitmap we keep on persisting to the disk at regular intervals. And what happens is that once that a new server comes up, right? Like it has to read like all the segments and the bitmap, and like it first recreates the metadata, and then like it begins the consuming process. So that's how it works. So the it leads to an increased basically startup time, but generally like it takes around like a few minutes at max. And like once they start, the metadata is recreated, then like it's again like as if like nothing died, and like you can simply start consuming from scratch.
Got it. Yeah. Makes sense.
Cool. So another like thing is like how what were the initial implementations of Upsert? So initially, like we were simply using like a key value stored for this metadata and like per server hash map, which was like if you think about it, that is the most obvious thing like people would do, like if you have to design something like this. But sooner, what we later realized, like it was extremely slow. First of all, like metadata update had to involve a network call to the KV store, and like the KV store itself, like was not really able to scale because it was shared across like all the servers. So we had to like come up with a different approach, and that's when we like after some brainstorming sessions, we ended up with the implementation I just showed you. Now, one caveat of that implementation is that basically, since the metadata is kept per server, right, you have to always ensure that if a primary key is published in Kafka, it always arrives on the same server. So, for example, if data is for primary key one and it is the old data was on server one, so the new data should also go on server one. Otherwise, what will happen is that if it goes to a different server, and like it will say, okay, this is some new key, and it will simply like update the data when in fact it was not supposed to be updated. Yes, sure.
Uh, so how is the um, schema kind of managed or defined in this? Like, so is the engine also aware of the schema registry in Kafka? Like, what sort of events?
Yeah. So basically, schema can be defined in two ways. So not always, like you have to explicitly define a schema for the Pinot table always. And in that schema, like you mentioned the columns, what are all the columns are there? What are the data types for each of the columns? And if it's, for example, string column, you'll have to mention like what is the maximum length of the string column can be. If it's a date time column, you'll have to mention like what is the format of the date in this column so that we can parse it out. And as far as schema registry is concerned, we use it for the parsing of the data. So while configuring the consumer in the table, you can specify like, please use this schema registry from the Kafka. Here are the basically whatever URL you have to give and the security configs, and like it will simply fetch the schema and use it to like decode, basically deserialize the data, whatever is coming from the Kafka. Yeah, so let's see some basic example of upsert, like how it occurs. Yes. So let's assume we have the data in following data. We have one segment which has like three rows, and the our primary key is basically the order ID column. So it has three unique rows which separates data created, assigned, and this is it says it is sealed. So sealed means like this has been published to the disk as a tar file, and it can't be changed. Okay, as simple as that. And the second one just has one row and it says mutable. So what that means is that like this is the data that is still being consumed. And if you want to change any row in this segment, you can like since it is in like mmap backed file, you can just simply update the row. Like you don't need to like basically do the whole operation of like reading and writing again. Next thing is that like we have that bitmap. So with the bitmap for called valid doc index. So for segment one, it says like all the rows are valid, which means they are in latest state 0, 1, and 2. And for second segment is also says okay that has one row and like that is valid. So it's a zero row. And then we have the metadata in the upsert. So the metadata is simply pointing out basically what is the latest location for each of those primary key. So for example, it says for AA, primary key AA, the latest data is located in segment 1 at row 0. And for primary key BB, it's located again in segment 1 at row 1 and so on, like for each of these segments. Now, let's say like we receive a new row. While consuming the primary key is BB, but the status is different. So that means like we need to update this row. What we'll do is that in the valid doc index of like the first segment, we'll simply remove the row 1 because it is now not in the latest state. The segment 2 contains the latest data. And in the segment one's bitmap, we added the row 1. Okay, you have the latest data for this key. Then in the metadata as well, we made the change. So for example, earlier it was BB was pointing to segment 1, row 1. Now it starts pointing to segment 2, row 1. Okay, and this is where your data is located. Now let's see, we received another data for a key E. Now the EE key was itself in this like mutable segment, right? Like it was not in the sealed segment. So what we'll do is that like instead of making like basically modifying these uh, metadata for the immutable ones, we simply like just update the value here. Okay, let's just point it out to row 2 in segment 2, and that's it. And once like this operation, for example, we received another row, is that delivered, right? We received another row, okay, and then like we'll update it and like once we have consumed the data, we'll seal it, and seal is simply pack it into a segment file and like we'll again publish their metadata and bitmap and everything to the disk for the creation. So now what is the V2 engine basically? So in Pinot, right, like one of the major ask from us was like we were not really supporting like we did support joins, but the way we supported joins was not scalable. So how we did joins earlier was like basically we had uh, you had to create like for example if you have to join two tables, so one of those tables need to be a dimension table and like that could be like contain for example just 100,000 rows or something, and we always used to keep the data for the dimension tables in each and every servers and inside the like not in the memory specifically, but it had to be in each and every server because the reason for that was like we don't really support like didn't really support like exchange of data between the servers. And so if data can't be exchanged between servers, then it simply means like if you have to do a join, then all of the data that needs to be joined should be present on that server. And like as you can simply think like that is not really scalable. But what if you have like 100 million rows? You can't really keep 100 million rows again and again on every server. The whole point is that you should be able to horizontally distribute that data. So and the second like blocker was like all of once we did any queries, all of our query, whatever data was returned by the server came to the broker, and the broker had to do the operations of reducing. And that reducer operation like took a lot of time and like because it was simply operating on a lot of data and on a single node. when each of the servers were operating on a subset of data. So we realized like this architecture was not simply scalable, and we moved on to like V2 engine, where we focused on like how to support more use cases in the query engine, like even like more types of join, and like how to make it more scalable. So in the V2 engine, what we came up with is the idea of two new component. So one was the data exchange layer, and the second was the intermediate stage. So what each of these does is that like the data exchange simply allows the servers to basically route data to each of them. So for example, it can real-time server one can route the data to offline server one for some joins. Offline server one can route some data to real-time server two for joins, and so on. And what intermediate does is that like it takes the responsibility away from the brokers to do all the reduce operations. And like that layer, like it's designed in a way along with the data exchange to be horizontally scalable. So you can simply like basically it knows like where all the data is coming from, and like it can, if it doesn't have whole data, like it can pass it to some other intermediary server, and like that can proceed with the next set of operations. And like once once any server has the final results, it simply returns it back to the broker. So for this, like we had some challenges. First of all, the challenge was like how to design the data exchange to be really fast, because we do need to shuffle like GBs of data around like in a query. So for that, what we came up with was a implementation based on gRPC. And in that implementation, what we do is that like each of, you can think of it as like a mailbox, and basically each server has a mailbox which incoming ID and like outgoing ID. And you can simply like any server can post a message, okay, publish this message A to mailbox one, and like whichever server is listening to that mailbox will like pull the data and like do whatever operation it's supposed to do. The second challenge was the like scaling the intermediary servers. So for that, what we did was like we didn't really want to introduce a new component into the mix, because we already have like 5, 6 components. So we created a sort of like an abstraction inside the servers itself, so that the servers can do both of these responsibilities at the same time. Like it could basically shuffle the data around. It could run the queries as well as it could do the reduce operations as well. Yeah. So, and then like we rewrote our like the query planner to basically support like this new like architecture. So initially a query planner was like a simple, like it would scatter the data and like gather it back. But then like we rewrote it to run it in multiple stages. So to like basically make the query latency is faster, basically. Yeah. Yeah. And the next thing that we had to do was like maintain the backward compatibility as well, because without backward compatibility, you can run into issues. Like we had like a lot of use cases already being done with the V1 engine. And if we didn't make it backward compatible, then like we'll have to support both of these engines. Like we didn't really have a choice. And that would like add a lot of pressure on the devs as well to maintain both of these features, maintaining the feature parity between these two. Then you'll have to basically ensure like if some, for example, mm, some new performance bottleneck arrives like in server, for example, query engine one, do you need it to be solved in query engine one, or do you need it to be solved in query engine two? So to avoid that, like we decided like we spent around a year on that to make it like fully backward compatible, so that we could permanently deprecate the V1 engine and like just use V2 for everything. We also had to ensure like this new architecture didn't really lead to increase in the query times for the simpler queries, although it can support the complex query. And that was also one of the problems we faced initially, because as you can see, like this has more steps, right? So if you are running the join query, then it's fine. But what if you are running a simple select query, like select star from table where column is equal to one? So you could face like a lot of data due to exchanges being occurring like in this architecture. So we solve for that as well. And finally, like we have it live, and like most people use Vito only right now. Yeah. So one of the let's see a simple example like how it works. So for example, like you have this query, select UID, R name, LTV from order status table, and you join it with the customer table on user ID. And then you have two filters where IC is item count is less than 10 and like lifetime or order count is greater than 5. So what will occur is that any query, as I mentioned, like will first go to the broker. The broker will create the plan for it. So what plan it creates is basically it divides it into three parts. The first part is basically select from table one, which is the order status table, and that is assigned to real-time server one and real-time server two, as you can see in the bottom left. So it assigns select UID R name from order status where item count is less than 10. So this is just a simple query, and servers can already execute such queries. Now the second query it is broken down into is the basically the for the customer table where we select the customer column, lifetime value, and the customer ID, and like to apply the filter where lifetime order count is greater than 5, and that we assign to another set of servers. Now both of these queries, when they are completed, they will transfer the data to the data exchange layer. Uh, what happens is that now we have the third query in the intermediate stage, and that does the join operation basically. Now that join operation, you can notice a caveat. It says local join. What local join means is that like the intermediate stage assumes that it has all the data for a particular user ID, for example, in this case. So if a user ID is one, it will simply assume it has all the data for user ID one, and like it will do a join basis on that. So, and the responsibility for that is on the data exchange layer to ensure that whatever data is for their user ID one, it always gets assigned to the same intermediary server. So it doesn't get assigned to any other intermediary servers. Yeah. So this is like the example, how first stage occurs. So for example, first stage selected these few rows and for order status table and customer table. Then what will happen is that that data will simply go to the data exchange layer. Now what data exchange layer is doing is that like it is assigning all the data for UID 1 to intermediary server 1, for UID 2 to intermediary server 2, and for UID 3 to intermediary server 3. That is the shuffle operation that is occurring on each servers. The next step is like the local join, as I told. So the intermediate servers will perform, since they have all the data for the primary key, right? Like they will perform the join operation in between them. First, intermediate server one only has order status data and no customer data, so no need of join. The second server has the data for both order status and customer, so it will join the values together and create all the combinations that are possible, and same will happen for server 3. Once you have that, like each of these servers will again go to our new data exchange layer, and like that will transfer the data to the broker. Although like it more often than not, like it just directly sends the results back to the broker. Yeah. So that is it. You have any questions?
Just a observation on the server side. So at any point in time, they might be processing multiple queries from the
Yes.
broker. So
Yes.
I mean, all these operations which we saw in the example, they're kind of all queued up, right? So different queries might be looking for different data, and like there
Yes.
might be
Yes. Yes.
queues on all
Definitely.
these servers. Yeah.
Yes. Yeah. So we just do like basically we have like multi-threaded operations, then we have we, as you mentioned, right, we do have like individual queues inside the server. So it can definitely happen like you ran a heavy query on one table and like it affected some other query on some other table. So that
Right.
you will have to manage by distributing the data appropriately, like, or like optimizing the query by indexes so that they don't do any like heavy thing.
Got it. And the
Uh,
engine also
yes.
like kind of
Yeah.
like most of the other storage engines also like flags any slow queries if they kind of go out of SLA or something.
Yeah, so for that, like we publish a lot of metrics with each query, and each of those, like we publish like how many scans occurred for this query, how many filters were actually queried, how many indexes were queried, or how much time did it take to shuffle the data for this query, and so on. So,
Gotcha.
like, yeah, so the on the basis of that, like people can take action, like, okay, we what do we need to really optimize in a particular query and not like waste their time. Yeah.
And does this happen only like in a special debug mode, or does it happen
No,
for
no, it
all?
happens by default. So in there's a special debug mode as well, and in that debug mode, the that info is a lot deeper. Like it will tell you
Mhm.
which exact server did which exact operation and which led to this slowness. But that introduces a latency in
Yeah.
itself because you have to like log so much information. So we keep it
Got it.
disabled by default and only just publish the matrix and
Hmm.
nothing else.
I see. Okay.
And Abhishek had one question. How would the data skewness be handled across the servers if a primary key always lands in the same servers? Yeah, so that is yeah, basically a design like a choice that you have to basically deal with it. Like if you, for example, you need to distribute your primary key. So a single primary key will need to arrive always in the same partition. But if you have like 100 million primary keys, you can distribute them to like 16 partitions or whatever you want. And like then that way you can ensure like basically the data is evenly distributed. But yeah, that is one of the basically fallbacks of that design, that you have to basically manage that partitioning scheme on your end rather than on the Pinoy. We are working on that, but so one implementation we have is the off-heap upsert, where we allow like a lot, even if you have data skewness, like it's not really a problem because it scales up to a billion or more primary keys per server. But in parallel, we are also working on some other approaches to solve for this.
Uh, I have a general question.
Yeah,
Um, like when we work with offline and I mean real time and offline data.
yeah, yeah,
So in one case, the data is kind of really fresh, and the other, we are like kind of working with a historical view.
yeah,
So like, how would like how do the queries work, or how do we like let the user
yeah,
know that you are working with historical
yeah,
data, or like a combination of real time and
yeah,
historical?
yeah. So what we do is that we have a concept in Pinot called hybrid tables. And what hybrid tables do is that like they create two separate tables, and one is the offline table and one is the real time table. And you can have different indexes on the offline table and different on the real time. And like but at the query time, you don't really need to specify from which table the data needs to be queried. You just need to mention the table name and like it will pick up the basically data from the appropriate location. And even in the basically whatever the queries you are firing, you can mention, okay, please mention me from where you actually read this data
Hmm.
for this row. So it will mention the segment name, the row number, everything. Like you can use that to basically optimize like whatever queries you want.
Got it. Got it. But
Yeah.
the end user needs to be aware that they are kind of joining with historical data. So the user needs to take care of
I
freshness.
think like they really do not, because the query, the if you are concerned about freshness, then yeah, like, but if you are concerned about latency, then no. Like
Hmm.
latencies will be same in both cases because we don't really do anything special like in the backend for like real-time tables. Like it is exactly the same as offline table.
I see. Yeah, makes sense.
A general question, when should Pinot be not used? A comparison with the data. You should not use Pinot. For example, you have like some OLTP use cases where you want to, you should use MySQL, Cassandra and stuff like that. If you have, although we are working on it, like if you have like, for example, extreme use cases where you need to require, for example, something like Datadog or Prometheus. So you should not use in those cases. Yeah, these are just a few ones. Mostly it is designed like the main use case we are targeting is that you have real time data. You want to run analytics query on top of it, and like you want those queries to run in milliseconds. Like that is the main use case. And like obviously at like really low cost, you don't want to spend a lot of money doing that. I'm not really familiar with the TIBCO Streambase, so sorry, I will not be able to answer that question. We also have an article on like comparison and like in which like pros and cons of like even Pinot and like other databases. So you can do that. Cool. So yeah, so you can try Pinot. You can go to our website. Then we have our SaaS free trial as well, which you can just do a single click to launch the cluster and like free of cost and like try it out like on whatever data you have. And you can also join our Slack. We are like pretty active there. Like we have like around 4,000 people active in the Slack, and like almost every query like you have like will be answered instantaneously, like almost like max 30 minutes. So yeah, cool. Thanks a lot, everyone.